I think some of you were in my electromagnetic wave class, so you knew my style of teaching. I want to get you involved, and I want you to have a lot of discussion. And occasionally, if there's a typhoon, we can go to the cafe. That was really good, right? But if it's a big size of the class, I can afford to pay you the cafe and also snack and so on. So it's always good that we have a small class. And in fact, we could have class in the cafe. Why not? If the class is small. Okay, we'll see if we could further reduce the size of the class. Then we can have the class in the restaurant. All right. So this is the sort of review for electromagnetic wave, and that is a very basic part of optics. So I have to go through this. And again, if you go through the first chapter of the H optics, then you see very detailed description of the electromagnetic and electromagnetic wave. All right. So last time we more or less looked into brainwave, and everything starts from this Helmholtz equation. If we are dealing with harmonic wave, so when we talk about harmonic wave, this means that we'll be dealing with this kind of wave or some phase, and then k dot r equal to a constant. Give you a plane in space, okay? A big plane in space. So we call this a plane wave. And this is one of the solutions of Helmholtz equation. Remember that you have many different solutions from this Helmholtz equation. But when we write down Helmholtz equation, we specify the field has a sinusoidal dependence. OK， 也就是说我们在写 Helmholtz equation 的时候，已经告诉我们自己说，这时间的这个的变化呢是正弦与弦函数的这种变化。So whenever you identify that the wave has such a sinusoidal variation in time, then you start with the Helmholtz equation, and one of the solutions will be this. But not all the solutions. This is not the only solution. Be careful that there will be other solutions, not just the plane wave solutions. But this solution is most convenient when we deal with Fourier optics. Therefore, we pick up this solution and then understand everything about physics. Okay, and when you do Fourier analysis, you understand that if you have sinusoidal functions, you can use the sinusoidal functions as a basis to synthesize all kinds of signals. And this is also the basis of linear theory or linear system. 在电机系里头，线性系统跟讯号处理的时候呢，我们都是用 sin、cosine 把它加出各式各样的波形出来。所以呢，这也为什么在讨论电磁学的时候呢，会把平面波这种弦波拿出来当做最简单、最基础的解。Okay, so this is the sort of very quick summary from by using memory. All right, so when we write down this expression, this is already understood. So if we continue to write it, then we can have arbitrary propagation direction for k. The plane of the plane wave, basically the wavefront can go in any direction. So we give three components for this k vector. With these three components for this k vector, then this means that if this is indeed a solution, then you put it into Helmholtz equation, then there's a condition need to be satisfied. That is k squared has to be square of the square sum of the three components. So this is a condition for this to be a solution of this expression. Okay, and so you start to see that if you have some Gaussian solution, and then it has to satisfy this Thomas equation, there's a certain condition it has to satisfy, and this condition is going to be used later. Okay, when we set the propagation directions. Okay, because this is relevant to the propagation direction of the plane wave. All right, R is just a position vector. So now this is understood. If this is a solution, then this has to be satisfied. So this is the logic. Okay, we guess some solutions for this one, and then we write K vector into 3 components, and the 3 components have to satisfy this condition. So this is the very simple and quick summary for this logic. Now, if you are not comfortable with the complex analysis, well, basically, complex analysis is just some kind of language. You speak in Japan, you speak in France, you speak in UK, you use different languages. And complex analysis basically is the language to describe, to calculate some physical phenomena. But after all, you have to, well, if you live in India, you have to go back to India. If you live in Taiwan, you have to come back to Taiwan to back to the reality. Then how do you go back to the reality? Well, it's simple. You just multiply this phasor expression, the solution of the Hamilton equation, with exponential j omega t, and take a real part of it. And then you come back to the reality. Okay, you go back your home to experience your life, okay, to restore your life. So the process is that once you have this phasor solution, you multiply this with exponential j omega t, and then you come back to your real life. That's it. Okay, so this is sort of some sort of process or steps we have in our life, right? We have some abstract thinking, and then we have a tool to get a solution, but then we have to go back to the reality. Okay, so this is the process that you go back to the reality. So this is something you can measure by your instrument. Okay, so once you finish the phasor calculation, you come back to the reality by multiplying this exponential omega t and take real part of it. So a plane wave is going to look like this in real life. Okay, and then geometrically, it just means that well, if you have to find out the wavefront, then you do this dot product. You do this dot product and set it to be constant, and you find that again, this is a plane. Because k dot r equal to a constant defines a plane in space. If just look into this dot product definition, it means that you are projecting this position along a fixed direction. And this projection has to be equal to a constant. And indeed, if you project this line on this, if this is a position vector on this plane, think about that, you project this onto this. Indeed, this is, if this direction is along the surface normal of the plane, then you have a fixed length, right? Remember that when you do like a dot a n along some direction is a constant. This means that you're projecting your vector a onto a n direction, and then you project it along this direction, and then this length is a constant, is a fixed. You project this onto this direction. This is the definition of the dot product. Everybody remember this, right? So you project this onto a certain direction. Is a fixed length. So this means that the next vector project along this direction also fixed length, and the next vector also project onto this direction is the length. So this means that you're projecting all the point on this line along this direction that has a fixed length. And then imagine that this is three-dimensional case, so we have a plane defined by this AN. This AN basically just the surface normal direction， 对吧？从几何上头可以看得出来，你如果是把任意的这个 position vector， 投影到某一个方向上头，然后呢是一个固定长度的话，那你开始就画出这个面了，你就得到这么一个面。那这个面就是什么？由这个 AN 定义的一个面，就是。The surface normal direction is defined by this AN. This AN defines the surface normal direction of this plane. Well, if we come back to here, this AN defines the surface normal direction of this plane. So this means that the K vector is along the surface normal direction of this plane. So now we understand that a plane wave is that you have a set of wavefront, and K vector is along the surface normal direction of this wavefront. Okay, I hope that you have this physical picture. And your eyes will be focusing on the wavefront when you say that, hey, the water wave is moving. In fact, what you're saying is that the wavefront is moving. Okay. So is this good? Everybody can create such a picture, right? 能理解吗？你如果有一个这个 position vector 投影到某一个方向上头是一个固定长度的话，那把所有的位置都把它连起来之后呢，它就形成一个面，然后这个 AN 就定义出这个面的垂直方向。Okay. Alright. So now you know how to construct the wavefront, and geometrically, in fact, you can define so-called direction cosines. Well, if you write down K, if you project K along x direction, in fact, you have Kx. So if you project this K along x direction, you have a Kx. Then there's a projection angle. Similarly, if you project this K along y direction, then you have a projection angle beta. Well, same thing if you project the K along z direction, then you have a projection angle gamma. So now you create a very nice physical picture here. Ks, Ky, Kz in terms of the projection angles, and we call this direction cosine. Okay. And but the angles are not arbitrary. The angles are not arbitrary. Why? Remember that if we have a plane wave solution as we define, then we have kx squared plus ky squared plus kz squared equal to k squared. Right? This is the condition we have right here. If this is going to be a solution, this condition has to be satisfied. So if we put it into such a geometric construction, then you have cosine square alpha plus cosine square beta plus cosine square gamma equals to 1. So alpha, beta, gamma are not arbitrary. You cannot write arbitrary angles here. This has to be satisfied. So when you define alpha and beta, you need to calculate gamma by yourself. Okay, from this expression. You can just set arbitrary numbers. Alright， 这样可以理解吗？就是 alpha、beta、gamma 是不能乱选的，你可以选其中2个，第3个必须用算的算出来。Okay, but this is very nice that you have projection angles and you start to visualize that this is a way that you sort of creating a physical picture for a plane wave. Okay, and so if you want to express the harmonic wave solution in terms of alpha, beta, gamma, it's going to look like this. We pull out the K, we pull out this K and write down cosine alpha, beta, gamma. And then now once you have this form, you can just draw your wave in the XYZ coordinate system. And it's a very nice visual illustration that if you can just draw it in the XYZ coordinate system. So you have three-dimensional picture for that. Okay, is there any question? Well, this is the review. I think most of the students, well, at this point, 30–40%, no, one half of the students in this class have gone through the electromagnetic wave, right? So you I knew that you are in my class now. 其他人都学会电磁学了，这是个 good， 所以还算容易，哎。好，那electromagnetic wave is a little bit tedious, but in fact, if you could just use the physical picture to fit into the solutions, then it's not so difficult then. But now we need to go through the little bit mathematics. Okay. Well, this is the vector calculus identity. Curl of a scalar multiplied with the vector can be calculated by this partial differential equation. Okay. By this differentiation by plots. Differentiation by plot. You first do the gradient of f and then cross with g plus f multiplied with curl of g. So if you apply this formula, this identity, vector identity into such the plane wave solution, then you end up having these results. Okay, you end up having these results. And this result is not so difficult because basically you just take this plot outside and right here. Okay, so you get this very simple result if you have a plane wave solution. Everything starts from this, and then you end up having this for your curl operation. All right, and but you have the Faraday's induction law. If you still remember the Faraday's induction law, you have curl of E equal to minus partial derivative B with respect to time. But now, if you convert this into phasor notation, you have E phasor notation equal to much J omega mu H phasor notation. Okay. Basically, this part is converted into J omega. Okay. And then don't forget that now you still have your differentiation with respect to the spatial coordinates. Okay, this part still retained. Only the temporal part is simplified. Okay, therefore we have such an expression here from the Faraday's law, Faraday's induction law, and with this, if you combine with this expression, okay, just put this, you combine this. Just put this into this location, take out this, and put this into this location. You end up having this relationship. And there's a prefactor in front of this E. That is 1 over eta. 1 over eta. Eta is the intrinsic wave impedance. In vacuum is 377 ohm. So you went through this when you study electromagnetic wave. Okay. But this also defines the directions relationship between AN and H and E and H. It does not specify the direction of AN and E. Remember, when you do this cross product, it tells you that the H is perpendicular to AN, H is perpendicular to E, but there's no information about the AN, the direction of between AN and E. So be careful, right? So by definition of the cross product, it tells you the relationship, the directional relationship between H and AN, H and E, but not quite the information about the directional information between these two. And remember this AN, that is the surface normal of the wavefront. Okay. All right, you can do the same thing to the Ampere's law. Well, if you just remember Ampere's law is equal to in free space. Previously we have this j, but now in free space we take it out. So you have this Ampere's law, and you convert it into phasor notation. You have this. Okay, and then you end up having this result. So you have more information. Okay, previously you knew that this guy is perpendicular to the surface normal direction of the wavefront, and this guy is perpendicular to the electric field direction, but we did not know the direction relationship between these two. But with this, now you understand, this guy and this guy, they are perpendicular to each other. Okay, and they follow right-hand rules. Okay, if you, for the first vector, you use 4 fingers along the 4-finger direction and cross with the direction of this, and your thumb is going to point to this, the third vectors. All right, so we start to construct the relationship between the magnitude of the field. At the same time, we also start to construct the directional relationship. And magically, there's a prefactor in front of it. That is very important. Okay. So basically, this eta is a ratio of electric field to magnetic field, and this number in vacuum is 377. But in optics, we deal a lot with direction material. Okay. If you have the wave in the direction material, then you have permittivity. Okay, and we define the permittivity to be define the refractive index to be the square root of permittivity, and we call this refractive index of the material. Okay. So in the material, the intrinsic wave impedance is going to be equal to the vacuum intrinsic wave impedance divided by the refractive index. When we use optical performance, we need to sort of add that into consideration. Okay, another thing you can use to figure out the direction relationship among all the vector components by using Gauss law. The Gauss law is, previously you have divergence of E equal to rho, but in free space this goes to 0, so you have divergence E equal to 0. Right, so if you apply this, the divergence of E equal to 0, but if the material is homogeneous, then you can take out the permittivity. You end up having this result. Well, this result, it tells you that if you project E along the AN direction, you get nothing. Okay, the possibility is that you are projecting a vector along this 90-degree direction. If you project a vector along this direction, you get nothing, then this vector forms 90 degrees with respect to this. Agree? Well, because this vector is not going to be 0. When we deal with the electromagnetic wave, we're not going to deal with any electric field that is 0. If it's 0, then it's not interesting, right? If this is the something is there, and you project something onto some direction is 0, well, then it means that they are forming 90-degree angle with respect to each other. All right. So this is another directional relationship between E and AN. All right. So you have 3 relationships right here. This allows you to construct the physical picture of electromagnetic wave. Okay. Now you understand from these 3 relationships, E and H are perpendicular to each other, and these 2 are also perpendicular to the K direction. Okay. But then you follow the right-hand rule. The K direction, E cross H direction is going to be along K direction. So physically you can draw such a diagram. Electric field, because we are using phasor notations, so we know that it is oscillating sinusoidally, okay, along this direction, and then we have oscillation of the field along this direction, and it's propagating along some direction. But if you flip the direction of E and H, then K will also flip the direction. So make sure that you understand the relationship, directional relationship. But if you care about the ratio of electric field and magnetic field, then you have to pick up with the wave impedance. Okay, you have to do this the ratio calculation with the intrinsic wave impedance. All right, any questions so far? So this is the to establish some background for you to study optics. Right. So now let's simplify the discussion by specifying the wavefront propagation direction along the z direction. Okay, and z direction is defined by us. So suppose that we don't deal with the propagation like this, or propagation like this. We deal with the propagation of wave along this AN. We call this z direction. Just to simplify the physical picture. Okay. And because the electric field and magnetic field are transverse to the propagation direction, we call this TEM plane wave. Transverse electromagnetic wave, or TEM wave. Okay. And with this simplification, we can take out, there's no variation of the field along the transverse plane because it's a plane wave, it's uniform. When we take out this, take out the x and y coordinates, okay? So we end up having this very simple Helmholtz equation depending on the z direction, okay? Depending on z direction only. Then we can write down the solutions of this one to be like this, and then the solutions of this one support this minus sign as well as support this plus sign. So there are two possible solutions. So you write down an expression including all possibilities with some amplitude over there. Be careful that when I write this negative sign, I put the plus sign here. When I write this plus sign, I put the minus sign here. Because later you're going to see that this represents a wave propagating along the plus z direction. This represents a wave propagating in the minus z direction. Okay, so adopt this convention in my lecture. All right, so now you have very simple solutions for the harmonic wave with a wavefront propagating along z direction. Then, if you're interested in constructing the real signal expression, then you multiply it with exponential geometry, integrally product, get something you can measure. So this is sort of repeating the steps we had before, except that we simplify the discussion by specifying the propagation direction along z direction. Okay. So this is sort of a review of the review. And the wavefront moving velocity, which is called phase velocity, is the ratio of angular frequency divided by the wave number, and given by this expression. Okay. If this is in the material, then you're going to have relative conductivity in this square root, and the velocity is reduced. So last time we spent a little bit time to talk about why the wave will reduce in velocity in the material. Okay, that is because the electromagnetic energy interact with dipoles in the material, and it takes some time. Whenever you deal with energy, you always take some time to do the energy exchange. So you slow down the electromagnetic wave. So refracting index, again, refracting index is index to tell you how strong the electric field coupled to the dipole oscillation. Okay. Right. So the second term give a real form. Basically, we have two terms. The second term give you a real form like this. But then when you calculate the phase velocity, well, you get a minus sign in this equation. And when you do this calculation, you are seeing something moving along z direction, but it's reducing in z direction. So assume this is the z direction. I'm doing this. This means that my distance accumulated from my walking is increasing, right? But then if I calculate something negative, give me a minus sign, the accumulation of my distance in fact is reduced. Then what do you